In this video, we are going to be continuing our journey in understanding cross products. We're going to go through the equation of a plane, and finally, we're going to end off with something super cool, and that's the concept of duality in linear algebra. So let's get to it. Recall what the cross product is, first of all. So it's an operation that you do with two vectors, kind of like the dot product, but instead of giving a scalar value, the cross product gives you a vector. And that vector is going to be, the magnitude of it is going to be the area of the parallelogram that's created from these two vectors. And then the direction of this vector is going to be perpendicular to other two vectors. And specifically, you might remember this from physics, but this will also obey the right-hand rule. Now, I want you to focus on something that's a little weird. I have the unit vector in the x direction, I hat, and this is the unit vector in the y direction, j hat. When I take the cross product of these two vectors, notice how I get k hat, the unit vector in the z direction. All right, so that's something that's pretty cool. Notice how the area of this parallelogram, in this case, this is just a square, so 1 times 1 gives me a magnitude of 1. Makes sense that we get a unit vector as an answer. And notice how k hat is also perpendicular, right? Because it's on completely separate axes, perpendicular to the x and y axis. And so it makes sense that this is true. Now, how do we actually compute cross products with algebra? And here's the weird way you do it. So to get I hat cross j hat, what you do is you set up a determinant. And so the first row of this determinant is I hat, j hat, k hat. And then after that, the other two rows are just the two vectors you're focusing on, the coordinates of the other two vectors. So I hat in this case, it's going to be at 1, 0, 0. And then j hat is going to be at 0, 1, 0. Okay? And so the determinant of this matrix, well, what is this going to be? This is just going to be I hat times the determinant of 0, 0, 0, 0, 1, 0, which is just going to be equal to 0. Then this is going to be minus j hat times the determinant of 1, 0, 0, 0. That's going to be equal to 0, right? That's all going to multiply out to 0. So that term cancels out. And finally, you have k hat times the determinant of 1, 0, 0, 1. And so the determinant of this matrix is equal to 1. And therefore, you can see that as a result, I hat cross j hat is going to give me k hat. All right, let's do another example. And let's spice things up a bit. And let's say that instead of I hat cross j hat, what if I did j hat cross k hat? So j hat cross k hat. What do you think is going to happen? What is your prediction? Well, let's do it. So it's going to be the determinant of this matrix. So j hat cross k hat is going to be equal to the determinant of this matrix, where the first row, the entries are I hat, j hat, k hat. And then the other two rows are just going to be your vector. So j hat is 0, 1, 0, and the k hat is 0, 0, 1. And so let's begin. So this is going to be I hat times the determinant of 1, 0, 0, 1, which is just going to be multiplied by 1. So it's just going to be I hat minus j hat times the determinant of 0, 0, 0, 1. That's just going to be equal to 0. And then this is going to be plus k hat times the determinant of 0, 1, 0, 0. That's just going to be a determinant of 0. So overall, j hat cross k hat gives me I hat. Okay. And so there's a really nice way to memorize all of this. Okay. So the way you think about it is that you have I hat, j hat, k hat in like a clockwise rotation. And so if you take I hat cross j hat, you're going to get k hat. If you take j hat cross k hat, you're going to get I hat. If you take k hat cross I hat, you get j hat. And so this is the loop. However, what happens if I do things the other way? So notice what happens if I do this. So this is going to be the determinant of the first 3 rows are just going to be your unit vectors. And then after that, we know that k hat is going to be 0, 0, 1, and j hat is going to be 0, 1, 0. And so the determinant of this matrix is going to be I hat times the determinant of 0, 1, 0, 0, 1, 1, 0, and the determinant of this matrix is going to be -1. So we're going to get negative I minus j hat, and the determinant of 0, 1, 0, 0, that's just going to be 0, and then plus k hat times the determinant of 0, 0, 0, 1, that's just going to be, once again, another determinant of 0. So notice how k hat cross j hat gives me negative I hat. And so this is one of the properties of cross products. The order does matter. All right, the order of cross products does matter. So if I did j cross k, I would get I. But if I did k cross j, I would get negative I. And so notice how if I take I hat cross j hat, notice how I get a positive area, right? However, if I swap these, if I swap these, notice how the vector now points downwards. And so the way I remember this is that on the coordinate plane, if I have I hat and I have j, this is going to yield a positive cross product. All right, meaning that if I reverse this, instead of I cross j, if I did create j cross I know that, well, the vector would flip around 180 degrees, and this area would be negative. Okay, so your unit vectors essentially defines what's going to be positive and what's going to be negative. Another way you can memorize this is that when you have a vector A and you have a vector B, if A is to the right of B, then it's going to be a positive cross product if you do A cross B. But if A is to the left of B, then if you do A cross B, it's going to yield a negative value. Okay. Now let's get into the equation of a plane. And spoiler alert, we will be using cross products. So how do you define a plane? You might remember maybe the definition of a plane is that it's defined by three points that aren't on the same line. So it encompasses a plane, right? Because if the points were on a single line, then you can have like this plane encompassing it, or a rotated version of it. So all these points have to be on. All these points aren't contained in a single line, and that defines a plane. But another way to define it is that you have a point on the plane, and in addition, you can have a vector that's perpendicular to this plane, and this perpendicular vector defines the orientation of it. And so we can call this vector n, and we can call this point p, let's just say. So one of the properties, I guess you can say, is that, well, n, unit vector n, is going to be perpendicular to the plane. So whatever plane equation that we have, it's going to be perpendicular to it. So let's try to come up with an equation of a plane. So let's say that we have this point P right over here that's on the plane. And let's say that we have the normal vector n that's also on the plane. Let's say that we choose another point on the plane. And let's call this other point P prime. P prime has the coordinates x, comma, y, comma, z. So it encompasses essentially any point, any other point that you can pick on this plane, right? Any point that you can pick on it, I'll just call the coordinates. We don't know what it is, but we know it's on the plane. So it's just x, comma, y, comma, z. Now, if I form a vector from P to P prime, notice how it's going to be perpendicular to the normal vector. And so I can say that P to P prime, that's going to be perpendicular to the normal vector. And that means that, well, the dot product between these two vectors is going to be equal to 0. So P prime dot the normal vector is going to be equal to 0. So let's just do a random example. I'm just going to make this up. So let's say that we have a point on the plane, and I don't know, point P has the coordinates of 1, -2, and 3. And let's say that the normal vector is equal to 1, 5, 7. And we want to calculate the equation of a plane from this information. So we also know that P prime, which is just another random point on the plane, That's just going to have the arbitrary, coordinates x, y, z. So first we have to find the vector p to p prime. And that's simple enough, right? You just subtract each component with one another. So p to p prime, that's going to be equal to, well, that's x minus 1, comma, y minus negative 2, comma, z minus 3. And so if we take the dot product of this with the normal vector, we know this has to be equal to 0. And so let's take the dot product between these two things. So I'm just going to get 1 times x minus 1 plus 5 times y plus 2, and then plus 7 times z minus 3 is equal to 0. So this is kind of like the main equation that you might see in like a textbook definition, where you just have like the coefficients right over here representing the normal vector, and then the inside portion right over here just represents the vector from one point p to arbitrary other point p prime. And so all we have left to do now is just to distribute, right? And then so if we distribute everything, we should get something in the form of ax plus by plus cz is equal to d. So I'm just going to move whatever constant there is to the other side. So this is going to be x minus 1 plus 5y plus 10 plus 7z minus 21 is equal to 0. And so let's see what we can do. This is x plus 5y plus 7z. And now I have to channel my inner algebra. So negative 21 plus 10 is negative 11. Minus 1 is negative 12. I'll push that to the other side. And there is the equation of our plane. Now let's complicate the problem a little bit. So we said how planes can be defined by 3 points that aren't on the same line. So let's say we have 3 points. Let's call this one A, B, and C. How can we compute the equation of a plane from these 3 points? What do you think? So we can create a vector, right? Let's say vector from A to B, and when we can also create a vector from A to C. So AB, and then we have AC. And notice how if I take the cross product between two vectors, I'm going to get a vector that's perpendicular to this. And so I can manually create this normal vector that I have. And once I have the normal vector, I'll just choose one vector and then the other vector of x, y, z. So recall point P. Right? So once I have this normal vector, then I can use the same strategy that I did before. I know that this vector here and then the normal vector, they got to be perpendicular to each other. And so I can find the equation of the plane like that. So feel free to pause the video and try this out yourself, okay? 3 points, find the equation of the plane. So let's start. Let's find out the vector AB. And let's also find out the vector AC. And then we just have to take the cross product between them. So AB, well, that's just going to be the vector, let's see, that's 3 minus 1 is 2, 1 minus 0 is 1, 0 minus 2 is negative 2. And AC is going to be, well, that's 2 minus 1, that's 2, negative 1 minus, right, that's negative 1, and 1 minus 2 is negative 1. And so if I take the cross product between the two vectors, well, that's the same thing as taking the determinant of, and then I hat, j hat, k hat. I have my two vectors in here, so 2, 1, negative 2, 1, negative 1, negative 1. And so this is going to be equal to I hat times the determinant of 1, negative 2, negative 1, negative 1. So 1, negative 2, negative 1, negative 1, minus j hat times the determinant of 2, negative 2, 1, negative 1, plus k hat, which is going to be 2, 1, 1, negative 1. And so determinant of this matrix is going to be, that's negative 1 minus, and then that's going to be 2, so that's going to be negative 3, so negative 3i minus j hat, and then what's the determinant of this matrix? It's 2 times negative 1 is negative 2 minus negative 2 that's just going to be equal to 0. So just that, and then plus k hat times the determinant of this, which is -2 minus 1, that's -3. So minus 3k hat. And so this is going to be equal to our normal vector. So another way to write this normal vector is that -3 in the x direction, 0 in the y direction, and -3 in the z direction. Okay. And so now we can just take one of these vectors, and we know the dot product between them has to be equal to 0. And so this is actually something, I mean, we've seen this before, but this is something called point normal form. So the point normal form is going to be, well, notice how we have essentially our normal vector. So I can say this is the normal vector in the x direction multiplied by x minus the x coordinate of your point. And then this is going to be plus, and then the normal vector in the y direction times y minus the y coordinate. And then this is going to be plus the normal in the z direction times z minus the z coordinate at that specific point. And we know that's going to have to be equal to 0. And so using this, right, now that we saw the proof for everything, because we know the dot product is equal to 0, well, once you understand the formula, then it's just plug and play. And so let's say that for this formula right over here, I use point A. So x1 would be 1, y1 would be 0, and then z1 would be 2. So this is x minus 1 plus the normal vector in the y direction. So all of this is 0. And then plus the normal vector in the z direction, which is just this, and then z minus z1. So that's 2. And that's going to be equal to 0. And so -3x plus 3 minus 3z plus 6 is equal to 0. -3x minus 3z is equal to -9. And if I divide both sides by -3, I just get that x plus z is going to be equal to 3. And that's going to be the equation of the plane. And we can do the same thing for lines. So if you, let's say this is my coordinate plane, let's say this is the x direction, this is the y direction, and I want to find the equation of the line given 2 points, right? Well, of course, if we were given 2 points and this is equation of the line, of course you could just do y is equal to mx plus b. That's boring. So let's do it in the point normal way. So the point normal way is exactly the way we did before. We want to find a normal vector, aka a perpendicular vector to our line. And so after we find this perpendicular vector, we know that, well, the dot product has to be equal to 0. So given like a point, and let's say another point, let me just call this p prime, which has the coordinates x comma y, we know that p to p prime is going to be perpendicular to the normal vector that I have here. And so the dot product of this is going to be equal to 0. And therefore, if you actually do all the calculations, right, you're going to get that the point normal of the equation of a line is going to be a times x minus x1 plus b times y minus y1 is equal to 0. Where x1 and y1 are the coordinates of the point that you're focusing on. Of course, x and y is the coordinate of this supposed p prime that's on the line, and a, b represent the components of the normal vector. So let's see how we can put this to use. So let's actually do this, all right? This is going to be amazing. Let's say that we have this point right over here, 3, 1. And let's say that we have another point down here that's -2, -4. Let's find the equation of the line the boring way, y equals mx plus b. So the slope of this line is going to be -5 over -5, which is equal to 1, okay? So we can plug this into y is equal to 1x plus b, and we know that when x is equal to 3, y is equal to 1, and so b is equal to -2. Okay, that works. Let's do it the fancy way. So we can, let's say that we pick this point P. All right, so we're going to use the x coordinate of P and the y coordinate of P as the x1 and y1 in our point normal equation. Now we know that the slope is 1. So what's a perpendicular scope to this? Not scope, slope. Well, we know that in 2 dimensions, the slope that's perpendicular is just going to be the negative reciprocal. So the negative reciprocal of this is just going to be -1. All right, negative reciprocal of this is just going to be -1. Well, then the simplest vector, and I know this line isn't accurate because it doesn't pass through the origin and everything, just ignore that. But I know that if the slope is -1, then the simplest normal vector that I can use is, well, -1, comma 1. Notice how this vector doesn't have to be obviously on the line, right? It just has to be a normal vector, a vector that's perpendicular to it, because we know that the dot product, no matter where it is, as long as it's perpendicular, it's going to be 0. And so if I plug everything into here using these components as the x1 and y1, I get -1 times x minus 3 plus 1 times y minus 1 is equal to 0. This is just going to be some simplification. So notice how this creates 2. And if I subtract 2 from both sides and I add x on both sides, I get y is equal to x minus 2. Same as we got here. So isn't that amazing? So here are just some other properties of the cross product. So as you might have guessed from before, if we have 2 vectors a and b, well then if we take the cross product between them, that's going to be equal to the negative of b cross a, right? So essentially, the orientation of a cross b, well, if you take b cross a, then you saw from the unit vectors that, well, one produces a vector upwards and the other one produces a vector that's facing the opposite direction. And so this negative sign essentially flips this back so that both are pointing upwards and are equal to each other. Here's another property. Let's say if we have some constant and then we have a cross b. So we have a cross b multiplied by some constant. Well, that's just going to be equal to, you can write this a couple of ways. So you can write k times a cross b. So you can kind of absorb this into a. Or you can absorb this into b by saying this is just the same thing as a cross and then kb. So let's think about why that's the case. So let's say if I have vector a, and let's say if I have vector b. And so we said how the cross product basically gives us the area of this parallelogram. Okay, so then we can form vector a right here, we can form vector v, b right here, and so the cross product gives us the area of this parallelogram, right? Now if we extend b another time, so in this case, this right over here would be 2b, 2 times b. Well, notice how my parallelogram just doubles in area. So if I scale a vector by some constant, well then I'm just scaling the area of my parallelogram by some constant, right? And so what you'll see is that the area of, let's say, one of these parallelograms, let's just call this big A. Well then, if I did A cross 2B, well then the area of these 2 parallelograms would just be 2A, right? So let me just write this down. So if I take A cross B, well then my area right over here is A. But if I take A cross 2B, then I'm just going to get 2A, right? It makes sense that I'm just extending one of these vectors, so I'm just going to get 2 of these same parallelograms. And it doesn't matter which way I extend this. For example, let's say instead of creating another parallelogram down here, what if instead of creating 2b, what if I created 2a? So I will extend the a vector now by 2. So this right over here, this is 2a, right? But notice still how we still get another parallelogram whose area is a. So whether you extend it using vector b or using vector a, ultimately the cross product between 2a and b is going to be the same as the cross product between a and 2b. So cross product between 2a and b is still going to be equal to 2a. And of course, the obvious way that we can write it is that another way that we can write just the same thing, right? Another way that we can write the same thing is that, well, we can take the cross product between A and B, and then if we just multiply this area by 2, well, then we're just going to get 2A, right? So here's basically all of the properties of the cross product. If you have a constant in front, right, you're able to move the constant freely throughout the components, because at the end of the day, well, you're just extending one of these vectors, or the constant can be negative, so it's flipping it around, but the area is just going to be like a scaled version of what it was originally. All right. The next property, it might seem pretty trivial, and you're probably just going to be like, that's kind of obvious, but A cross A, if you cross a vector with itself, that's just going to be equal to 0. Think about it. If you're trying to find out the area of this parallelogram given the same vector, well, there is no area, right? And so the magnitude of this cross product is going to be equal to 0, which means that this entire cross product is just going to be equal to 0, okay? I mean, another way you can think about this is that, like, if you have two vectors right over here, then the cross product between them gives us a vector that's perpendicular to it. But if we just have a single vector, then there's going to be infinitely many options that are perpendicular to the same vector. And so everything is just going to collapse to 0, right? You obviously can't have infinite like solutions to this cross product. So it's just going to be equal to 0. We've been talking a lot about cross products, and there are still a couple of properties that I have yet to go over. But one thing that I haven't gone over is, what is the magnitude of the cross product? How can we calculate that? That seems pretty interesting, or not magnitude, magnitude of A cross B. How can we calculate the magnitude of a cross product? So in this case, we don't really care about the new vector that's forming. We only care about this area of the parallelogram. And so if I have this vector A and I have this vector V, well, I know that the area of this parallelogram is just going to be equal to the base of this parallelogram multiplied by the height. Now, how can I get this height? Well, I see this angle right over here, theta. And so I know that if I multiply, I just know that if I multiply the magnitude of vector A, right, the length of vector A, by essentially the height, well, I'm just going to get the area of the parallelogram, right? Parallelogram area. And so how do we find the height? Well, then, notice how we form a 90-degree right triangle. And so we can say that sine of this angle is equal to, well, that's equal to opposite over hypotenuse. And specifically, it's the magnitude of vector B, right, if we're treating this like a right triangle. And so the height is just going to be the magnitude of vector B times sine of the angle. And voila, we see that the area of our parallelogram is going to be equal to the magnitude of A times the magnitude of B times sine of the angle. So don't get this confused with dot products, because it does look very similar, but they're two completely, well, I wouldn't say they're separate, because the next formula that I'm talking about is going to relate these two together, but they're different formulas, of course, right? But the magnitude of the cross product is just a little different, okay? Instead of cosine, you're dealing with sine. So we can add this property to the list of our formulas that we have. Now the next one requires some extensive visualization. So let's draw this one out. In fact, if we think about the sine of this angle right over here, it kind of makes sense why, if we have a vector crossing itself, it's going to be equal to 0. Sine of 0, well, what's sine of 0? That's just going to be equal to 0, right? So if the angle between the two vectors is equal to 0, well, then the cross product magnitude is going to be equal to 0. In fact, any parallel vectors are going to have the cross product of 0, right? Because the angle is still going to be 0. So in fact, if you have A cross B, where A is perpendicular to B, well, then the cross product is going to be 0. So that's just something important to know, okay? So this one's pretty, it looks pretty simple, right? So A cross B plus C is equal to A cross B plus A cross C. This is something called, you might recognize this as some sort of distributive property. Like, it kind of looks like just distribute the cross and the A and everything works out. And this is due to the fact that if you have vector v, let's just say, and then you have vector c, and let's say this is vector a, I'll just do it like this. This is vector a. So notice how this new vector right over here represents the vector b plus c, right? Vector b plus vector c. And so if I take the cross product of these two vectors, so a cross b plus c, well, I'm just gonna get, well, let's visualize the area, right? So what I'm gonna get, I'm gonna get some area that looks like something like this. So something like this, okay? So that's a cross b plus c. That's the magnitude of it. Now, if I take a cross b, well, what's that gonna look like? A cross b, it's gonna be this area right over here, right? So it's gonna be this area right over here. And then if I have a cross c, well, then if I have vector a and I have vector c, it's going to be this area right over here. And then the sum of these two areas is going to equal the big area, and it's going to have the correct orientation. To explain why the orientation of the vector stays the same, well, look at this. Notice how when I move vector c around, I can move vector c as weirdly as I want. But notice how this vector that it produces, it's still perpendicular at the end of the day, right? When I add, let's say if this is vector a, this is vector b producing vector c, it's still, everything's still on the same plane. So that's why like the orientation of that resulting vector is still going to be preserved, even when we add two other vectors. Now here's where dot products and cross products really combine to create something amazing. And once you understand this, everything is going to make sense. You're going to feel like you discovered something amazing. So if I have a dot b cross c, what is that going to be equal to? Take a guess. So this actually has the property of something called cyclic permutations. Now, what the hell do I mean by that? So think about it this way, right? Imagine if we shifted everything 1 over. Imagine if we shifted all units 1 over. Then I would have b dot c cross a. Okay? And then imagine if I shifted all vectors 1 over again. Then this would still be equal to c, and then you would have a cross b. So this is what, so you might hear it like as cyclic permutation as like a fancy way of saying it. It just means like you can shift everything by 1 unit. So b goes here, c goes here, a goes to the back now. So you get this, and it would still be equal. And you can shift it again, right? So b goes back, c goes here in the place of b, a goes here, and it would still be equal. This is a diagram that's used to visualize what we have right over here. So specifically, it's this first portion where, or sorry, this last portion right over here, where we have a cross b, and then we take the dot product of that with the vector c. So let's see what that gives us. So this right over here is a parallelepiped, and notice how a cross b, the magnitude of this vector right over here, is the area of the base of the parallelogram, right? And notice how a cross b is perpendicular to the base, right? Now, we know how to find out the volume of this parallelepiped, right? So the volume of this parallelepiped, I'm just going to call it triple P, that's going to be equal to the area of this parallelogram multiplied by the height, right? And so notice how I can get the height. Because I have this vector that's perpendicular to the base, well, this can be used for the height because I have this vector c right over here. And notice how cosine of this angle is going to be equal to the adjacent side, which you can think about it as the height, right? Now I want to find out, divided by the hypotenuse of this triangle, which in this case is vector c, right? Because you can view this as a right triangle. Specifically, it's the magnitude of c. And so ultimately, the height of this is going to be c, the magnitude of c, times cosine of the angle. And so if you saw my previous video on components and projections, well, you know that the dot product essentially gives us essentially the component of C along A cross B multiplied by the magnitude of A cross B itself. So we're essentially multiplying by the magnitude of the base of the parallelogram by the actual height itself, right? And so this formula, all these formulas right over here, gives us the volume of the parallelepiped. And notice how this final dot product right over here actually gives us a scalar quantity, which is something that's important, right? Because we're talking about volumes. So it makes sense that this gives us a vector, and then when we take the dot product between the resulting things, well, then we get a scalar quantity to represent the entire volume, right? But what else do we know gives us the area of this parallelepiped? That's right, the determinant. The determinant of the 3 by 3 matrix, where you essentially have the vector A in the XYZ direction, vector B in the XYZ direction, and vector C in the XYZ direction. This is also going to be equivalent to finding out the volume of this parallelepiped, right? And so all of these are going to be equal to each other. And that is the amazing connection. So now you realize how cross products are connected to dot products, but they're also connected. So now this is the final topic. And this topic is something called duality. Okay? Duality and dot product. So what's another way that we can view the dot product? Right? When we have a dot product between the two numbers, let's say xy, let's say like 1, 2. The dot product is just going to be, well, in this case, x plus 2y. Another way to view this dot product is that this vector can be viewed as a row vector. So instead of this being a column vector, right, where this is just a single column, you can view this as a row vector, xy, and then 1, 2. And so when you get x plus 2y and you kind of view it from this perspective, well, you can view xy as a sort of matrix. And we saw how when we're dealing with matrix, this essentially defines a transformation. And you can think about this transformation as you're mapping a vector from 2 dimensions to 1 dimension, right? So this is just a way to map 2 dimensions to 1 dimension, kind of how you're reducing the dimensions when you're doing matrix multiplication, and sometimes it can collapse everything into a line. This is kind of like the same thing. And so what this is really saying is that whatever x and y value that we have, the y value is going to be weighted 2 times as much as the x value. And so if I set this equal to 3, well, this is basically saying, well, given a quiz score and a test score, find me all possible combinations where your final score, which is just the sum of the quiz and the test, is equal to 3, right? And well, you view this operation as a dot product, but you can also view it as a transformation, squishing everything to the number line. So you see how the unit vector, if you have a unit vector in the x direction, well, that would correspond to maybe a length of 1. So maybe this is where I hat maps to. But then if you have the unit vector in the j direction, well, then notice how since y is weighted 2 times as much as x, well, then j would be twice as long as I. And so you can view this once again as a transformation of the unit vectors. Just to make this video a little longer, I'm just going to talk about parametric equations. And so parametric equations, you basically have an x and y variable, and both of them are changing in many cases with respect to time. And so if you plot x and y as time changes, well, then you get this funky looking graph. So both x and y have this relationship where they're both related by the single variable t, and however, there's not an explicit kind of x and y function, right? It's not like f of x is equal to something, or y is equal to 3x or something like that. Both of them are kind of implicitly related to each other through the variable t. All right. So that's kind of like the basics of parametric function. And so a common example of this would be in physics. So you might recall projectile motion, right? Let's say if I'm on the roof of a building and I throw a football down, right? Notice how the height is changing with respect to time, right? It's accelerating downwards. So the rate of change of the height, right? It's going to be decreasing, 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 right? Going faster and faster and faster. On the other hand, assuming there's no air resistance, the rate of change at which x changes with respect to time, that's going to stay constant, right? If there's no air resistance and I initially throw the ball at, let's say, 5 miles per hour, not 5 miles per hour to the right, well, then in the x direction, it's going to keep on traveling that 5 miles per hour. However, in the y direction, you might recall that, well, the acceleration due to gravity is negative 9.81 meters per second squared. So the position of this ball is going to be constantly, constantly getting lower and lower, extremely fast, because we're accelerating in the y direction. While in the x direction, it's constant, okay? So it's constant, I'll just say motion, or constant speed, or velocity. So your change in position, if you have a constant velocity in the x direction, that means that your change in x is going to be a constant value, okay? And so we're going to be learning about, simple methods. So let's say if x is equal to t, and let's say if y is equal to t squared, something really simple. Notice how this gives us a parabola. And why does this make sense? So if x is equal to t, and y is equal to t squared, if I substitute x in for t, right, because x is equal to t, well, then I just get y is equal to x squared. So you can see how for parametric equations, you're able to convert from, you know, x is equal to t, y is equal to t squared into an explicit relationship between y and x squared. And we're also going to learn how to convert back and how to model equations describing circles. So how to use parametric equations to describe, sine and cosine. We're also going to talk about cycloids. So essentially, imagine if you have a wheel, right, that initially starts at the origin, and you want to model the position of a specific point as the wheel rotates around. So let me show you an example. So we are trying to model this blue point as the wheel spins around, and you can see how you get this hill-like shapes that comes from the cycloid. All right. So that's actually pretty nice, and we'll learn how to derive all of these parametric equations for the equation of the cycloid. Also note how there seems to be some kind of, I don't know, is there asymptote here? Is there asymptote here? I don't know. We are going to figure this out. We are going to find the limit as we approach one of these sharp points, and we are going to discover all the secrets of parametric equations. That's all.